So we hear the terms literally every single day, right? Algorithms, machine learning, AI. But if you look past all the sci-fi movie tropes and the corporate marketing buzzwords, how does a machine actually think? Like, how does this complete black box of code go from crunching basic numbers to, say, diagnosing complex diseases or flying drones? Let's figure it out. Welcome to The Explainer. Today, we are taking a seriously fascinating journey straight into the AI mind. We're going to break down the actual mechanics of synthetic intelligence. So we'll be moving from the foundational building blocks of basic algorithms all the way up to the wild, cutting-edge frontiers of neuromorphic and quantum computing. Here's our roadmap for today. We'll be defining the AI mind, looking inside neural networks, exploring processing language and vision, checking out agents in virtual worlds, and finally, wrapping up with the future of computing. Section 1. Defining the AI mind, unpacking the buzzwords. Okay, so according to IBM, artificial intelligence is basically the science of enabling computers to think and decide like us humans. It's really just a big umbrella term for systems designed to mimic human thought and decision-making. But keep in mind, artificial intelligence is just the ultimate goal on the horizon, right? The actual engine that gets us there, the process that simulates that cognition, well, that's a bit more specific. And that engine is machine learning. If we zoom in just one layer, machine learning is using data and algorithms to let systems learn and improve autonomously. Instead of some programmer sitting there typing out a million specific rules for what a cat looks like, the machine is just fed massive datasets of photos. It learns to spot the whiskers and the ears completely on its own. It's learning through exposure, honestly much like we do. This is a massive paradigm shift. Under traditional computing, machines relied entirely on explicit rules and manual programming. If X happens, do Y. But with machine learning, algorithms are extracting patterns directly from those massive datasets. We aren't just handing machines rigid instructions anymore. We're actually giving them the ability to learn the rules themselves. And that right there is the absolute bedrock of how modern AI actually begins to think. Section 2. Inside neural networks, the brain of the machine. So, the most successful architecture for machine learning is the neural network. This is the literal beginning of the thinking process. These are programs designed to recognize patterns and solve problems by directly simulating the biological structures of the human brain. In deep learning, these networks stack layers upon layers of processing nodes, basically synthetic neurons, to handle incredibly complex, unsupervised tasks. And as Pierre Labroche from Stanford's computer science department points out, decoding the brain's neural activity actually goes both ways. By building these synthetic brains and watching how they process information, researchers are simultaneously decoding and understanding the inner workings of our own biological brains. It's this really profound feedback loop of scientific discovery where our code is literally teaching us about our own cognition. And it is honestly stunning how precise this mapping has become. Recent research published in PNAS introduced the Functional Complexity Index, which quantifies the input-output complexity of individual brain cells. They found that human cortical neurons differ significantly from, say, those of rodents in their structural complexity. Why this matters for us is that today's AI models aren't just broadly mimicking a brain anymore. They're increasingly trying to map to the unique, highly advanced input-output complexities of human cortical neurons specifically. Section 3. Processing language and vision, senses and understanding. Now that we have a brain, the first primary sense it needs is language. Natural language processing, or NLP, is what transforms our messy, unstructured human speech into actionable data. You can kind of think of it as the machine's inner monologue and comprehension tool. This is exactly what allows an AI to essentially read a textbook, listen to a conversation, and then process that human language to form a cohesive understanding of a topic. But when you combine NLP with vision AI, which is the ability to process and understand visual data, the results are just staggering. AI powerhouses like Google, DeepMind, and NVIDIA are using these sensory capabilities to solve grand scientific challenges. Take AlphaFold, for example, which uses pattern recognition to predict protein structures with incredible accuracy, unlocking totally new avenues to cure disease. Or WeatherNext, which is providing insanely fast AI weather forecasting. By giving AI the ability to see and read, we've basically turned it into the ultimate research assistant. Section 4. Agents in virtual worlds, acting in the world. Right now, we are smack in the middle of a massive leap. Traditional AI passively absorbs static text, pretty much just sitting there waiting for you to prompt it. But agentic AI is an entirely different beast. It actively reasons, plans, and acts autonomously to pursue goals. We are transitioning away from bots that just chat to agents that can formulate an objective, create a step-by-step plan, and take independent action to actually achieve it. But how do you actually train an AI to safely act in the real world? Well, you build a virtual one. As noted by Science Magazine, researchers are developing agents that learn by acting in simulated environments. Take DeepMind's Sima 2 agent, for instance. It learns by playing and interacting in virtual 3D worlds. It enters the environment, it tests actions and makes decisions, and then it learns from the simulated outcomes. Honestly, it's exactly how a child learns by playing. The big takeaway here is that these virtual playgrounds translate directly to physical reality. Over at MIT, researchers like Andrea Henschel are using multi-agent reinforcement learning trained entirely in these virtual environments to program autonomous drones. These small quadrotors can rapidly and autonomously search complex, chaotic buildings for search and rescue missions. Think about that. The AI learned to navigate a physical building by failing 1,000,000 times in a simulated one, ultimately saving human lives in the real world. Absolutely wild. Section 5. The future of computing, the next frontier. So currently, we run AI on classical computer chips. But the future? That relies on neuromorphic computing. This is hardware engineering specifically designed to mimic the exact way the human biological brain works. According to IEEE Spectrum, researchers are now building simple, hyper-efficient physical devices that mimic the exact behavior of single biological brain cells. So instead of software just pretending to be a brain on traditional silicon, the hardware itself is actually becoming brain-like. And running right alongside neuromorphic chips, we have quantum computing. Classical computers use bits, ones and zeros. Quantum computers use qubits, which can exist as ones, zeros, or both simultaneously thanks to quantum mechanics. It's like spinning a coin instead of just looking at heads or tails. Tech giants like Google and IBM are utilizing these qubits to solve incredibly complex optimization and chemistry problems that classical computers simply cannot handle, basically processing massive amounts of variables all at once. These incredible advancements in AI software and quantum hardware form the framework for what DeepMind's Demis Hassabis calls the path to AGI, artificial general intelligence. And this is the holy grail. AGI models won't just mimic human intelligence, they'll be able to generate and explore entire interactive world models. They are literally being built to solve root node problems. I mean the fundamental mysteries in fusion energy, materials science, and biology. Which really leaves us with one final, kind of mind-bending thought. What happens to our entire understanding of intelligence when the gap between biological brains and synthetic circuits is completely bridged? It's something to think about. Thank you so much for joining me for this explainer. Keep questioning the technology that is actively reshaping our world, and I'll catch you next time.